Can you hear me? Okay. So good morning. So good noon. So okay. So in this module number 8, this is the 2-point boundary value problem. So sorry for the delay. And here, um, this is the summary, no, of what I mean is most of the modules that we have learned the past uh, meetings. We actually, uh, if we add them together, we will have this module, no, as the summary. Meaning, we the problems of 2-point boundary value problems need or requires the previous modules, no. So just in case you missed the previous modules, would like you to review again the module 7, from module 0 to module 7. So very simple, no, for the 2-point boundary value problems. Actually the same with the previous module, which is module number 7, which is initial value problem. But here, most of the engineering problems are bounded, meaning we have certain values, no, we would like from A to B. Just a moment. Meaning you have two auxiliary conditions of at two different values of x at A and B. And it's good to realize that most of the engineering problems do have boundaries. It is only in the numeric analytical methods in physics, in uh, basic sciences, that they try to prove things in general. Meaning, for example, the outer space, the astronomy, for example. So you need to show that mathematically the black hole existed, or exists, or maybe the wormhole, or whatever phenomenon, no, they try to express it mathematically, but they wanted it to be general, meaning it is true to all space. And in this case, the space is not only the um, from negative infinity to infinity, you can say, no. So from a certain point to a certain point, but in general, so they have this concept of infinity, no, so to cover everything. But what I wanted to emphasize here is that in engineering we have boundary, meaning if you want to build a bridge, of course there's no infinity on that, no. So from a certain point to 1 kilometer, for example, if you're making a bridge for 1 kilometer, no, and then you need to solve for the uh, well, maybe the the behavior, the dynamic behavior of your bridge, no. So you need to measure that one, but of course with the boundary at a certain point origin A to the end, which is B, no. So that's very important, no. And of course in engineering, we've learned analytically, no, in differential equations and optimizations, but all of these cannot cannot be solved manually, no. Imagine if you solve for the maximum allowable weight for a bridge. Of course you will not manually solve it, no, because for how many structural members, for how many uh, uh, so, and then also the geometry of these structures. So of course we cannot solve it manually, although we have learned the basic concepts, doing analytical, but we ask or we need the help of computers, no, to measure the behavior, the response, okay, of the system. For electrical engineering, we have problems such as the transient and also the step response and the general response of a electrical system. Okay, so 2-point boundary problem, this will be in this case sufficient enough if you are studying engineering numerical methods. If you reach this point, 2-point boundary value problems, then you've learned already the concept, no, of numerical methods. Although there are more advanced modules, module 9 and 10, and so on, machine learning, artificial intelligence, but here we are in the modeling numerical methods, meaning we are not we're using the aid of computers to model our system. Okay, now later on, the advance is the learning, the artificial intelligence. Okay, actually they're the same numerical methods, they have the same principle using um, different numerical method techniques, and of course, the program. Okay, they have the same, and actually we'll have it in the future, in the succeeding the next month probably we will have those lectures, but you will see that the same code, no, you have from the module 0 to module 8, so the same technique. Okay, now here, very simple. For one of the example of two-point boundary problem is a second order differential equation expressed by this one. Okay, so you have the x, and x is the so-called the independent variable. Okay, and y is the dependent variable, and you have the y prime, meaning the first order of the y. So you can imagine a velocity, no? So for example, you have velocity, you have displacement x. Okay, you have a displacement like this, no? So your car is moving that way. So the x, okay, is the let's say at time, x is the displacement, and y is your sorry, the displacement, and y is your speed, or maybe y prime or x prime. Wait, the distance, sorry, this should be the distance, and then this is time. Okay, and for sorry, this should be y. I'm sorry for that. So this is x, and this is y. So meaning your y is the distance covered, no, and then x is the meter. So meaning so displacement meaning from your point A, okay, to a certain point B, and this is your displacement. And y measures the, okay, this is your distance covered, and the y prime is the certain point. This is your velocity. Okay, and then so this is your y prime, this is your velocity, or y dot, y prime or y dot, and then your acceleration. Okay, you're accelerating, so you have also that one, so you have y double dot, okay, or y double prime. Okay, so the acceleration, so we've learned that one um, in our physics, no, mechanics. So the acceleration, velocity, and the displacement. Okay, and I think this is time. If I'm not, this should be time. Sorry for that. A bit confusion on. So this should be time t. Then this one is the displacement. Okay. Well, yeah. And then, so meaning, if they are bounded, so you have from A to B, you can measure the area in between. The area in between is what makes, if you can solve for the area in between, you can actually solve for any of those, no, y double prime, y prime, or y. So we will see it later. Okay, so here we're going to discuss the finite difference method. So although there are some other methods that you can use for 2-point boundary value problems, there are some a bit advanced, but here's a very simple one. Okay, so similar to the initial value problems, you have here the 2-point boundary value problems, meaning uh, you have bounded it is bounded a to b, and take note of the graph, no? So you have here the if you can see the graph, no, you have here from A to B. Okay, this is similar to the previous module. So we have panels, the m equal panels. So this is the step in solving this problem. So very simple. First, given range of integration A to B, in the above illustration, subdivided into m subinterval parts, each with length h. So they are in the previous module we call this the panels, identical panels, okay, divided by m. And then just there's a bit added the m plus 1 and then negative 1, just to add a bit, no? So you will see that you take the average of the 2 points, and this will be the height of this, no? So you take y1 plus later we will see. So the first one is you have the given curve, okay, bounded from A to B, subdivided into m parts. So it can be how many subinterval parts you want, okay, and then with equal h. So step 2, having done that, the derivatives of y in the differential equations are replaced by the finite difference expressions. So you have this one, no? Y I plus 1 minus y minus 1. So meaning if you start from 0, so the velocity, for example, okay, the velocity, you have uh, okay, I think not to confuse you with this, actually you can replace this one with x, and then this one y, and then you think of x as the time, no? Time, and then y is the distance, okay, so so that you will not be confused, no? So x is the time, and then y is the distance traveled. So at a certain time, so this is the distance traveled. So that we will have a concrete example here. So if you have at I plus 1, so I plus 1, this is your distance traveled, let's say 10, and then y I minus 1, so that would be negative 1 at I is equal to 0. So y1 and then 1 y negative 1, so the difference between the two, and then divided by 2h, okay, that will be your y prime. Now meaning y prime is actually, if you try to visualize it, you have at this point, no, and you have the 2, so this is your y1 and then y negative 1. So and then you have h. So you can see that this is actually the slope of the line. So y prime is equal to y minus, okay, this is actually the slope, okay, slope of at point y0. So this is at point y0, okay. So actually the slope at y0, so in between y1 and y negative 1, okay. So the slope, no, the slope, so that's the velocity at that certain point. And then y double prime is the acceleration, and you can observe that we have it's like the finite difference equation of y plus 1. So at I is equal to 0, okay, so you can think of it as like this, similar drawing, but you include the value of your y0. So y double prime is equal to y negative 1 minus 2y0 plus y1 divided by h squared. Now, where do we get this? Actually, if you can remember your acceleration, acceleration is, you can actually, how you call it? So actually, this one, and if we to one because this one is acceleration. This is similar with to analogy this with physics. So we have A is equal to uh, you can remember, sorry, it should not be A, so this is v squared, sorry, this should be x squared, I sorry, it should be v squared equals 2gh, and then no, sorry, and then g is the acceleration. Okay, and wait, I forgot already. So that and then if you replace this one, the v as your y, and then so a is equal to 1/2 uh, v squared over h. And if you replace v with this one here, you will see that uh, you will uh, the v with your y, you will end up with this. Okay, and um, you can also think that one as the actually physical meaning of that. We can draw it. Okay, so bear with me. So let's say this is short. So because um, you have h squared, so actually acceleration is the um, actually you have the two, you have assuming you have y, actually it's like the average of two velocity. At this point you have a velocity like that, and then at this point you have another velocity, and they are not the same. So let's say this is y prime of -1, and then y prime of 1. So it's like y double prime is equal to y prime 1 minus, or -1, -1, -1, and 1, so 1 divided by h. And then if you replace this individual y prime from this one here, to give you the, if you replace that one here respectively, then you will get here and here, you will get this. So you can just imagine you have h denominator here, and then you have another denominator h, and this become h squared, okay, which is correct. And then you have the above expression, the actually this we can solve it if you like. So y prime is let's say you assume that 0, assume that this is 0 here, and then minus y y0 over h, and then minus uh, y0, and then here you have y0, and then minus y1. Maybe this one here is y -1, and this is also divided by h, and then divided by h, and you will have y -1 minus 2 y0 minus y1. So this is y divided by h squared. So this is your y. So I hope this is the same. Okay, so this is the same. Okay, so these are the physical meaning of the finite difference expression. So I hope you can see the expression. Okay, and so we now understand this one here, and the same also for y. If you want to extend, okay, you can also do that. I minus 1, then minus I plus 1, okay, divided by h. Okay, so on and so forth. So this is what we call the central finite difference expression. Okay, so but most of the engineering problems, we only deal with with the first and second order differential equations. Seldom we will use the third order, and also more than third order we cannot use things like uh, we don't need the how you call it. It's not good to talk about it conceptually, but we can do it, no? Actually, most of the simulation, AutoCAD or whatever simulation you have, COMSOL, all of these are more than 1,000 of degree of freedom. Here we only have 1 or 2 degrees of freedom, and for most of the systems it's beyond thousands, no? Imagine a hearing aid has maybe 10,000 degrees of freedom, and you cannot solve it manually. Then we should use numerical methods. Okay, the only difference is that you cannot see the algorithm, no, inside the software, because first it is patented, second it's quite complicated, but once you know that it's only finite difference method or whatever method they're using, they can be solved, no, computationally. So that's why if you have a console or whatever simulation, you need powerful computers, no? The more powerful your computer, the more easier to solve, no? Because you can the computer can just solve it, no, on its own and very fast. Okay, that's a step 2, and I hope you get the point of y I prime and the yi double prime. Then step 3, the differential equation is enforced only in each mesh point. Okay, so this expression is enforced in each of the mesh. So y0 at I is equal to 0. Okay, at this point, what is the velocity? Or here, what is the acceleration at this point, and this point, and this point, until you get um, until ym. Okay, y prime m or y prime double prime m. Okay, so this step will result to m plus 1 simultaneous algebraic equations with unknown variables y I, which is from 0 to m. Okay, so unknown variables of y, meaning later on you will see the different expression. Sorry. So here you will have this expression, no, m and so, but I will explain this one later. So so there are m plus 1 simultaneous algebraic equations. So we have learned the algebraic equation in the previous module. I think it's module number 3 or 4. So you might want to check it out. So meaning actually very simple also, because from the word finite we actually convert the second order differential equation into linear equations. Okay, we actually convert everything into linear equations because the computer can only operate plus minus. Okay, actually the multiplication and division is simply add or minus, or division subtraction and addition. Okay, and we know that the computer is simply binary, so you just add something, no, add binarily, no. So everything should be converted into linear simultaneous algebraic equation. So linear, although it is in second order, but we approximate it into linear equation. So you notice here linear, although h squared, because h is is a constant value, so it doesn't affect the equation. So you notice the variable y, so they are in the first degree, no, so meaning linear. So we convert the function into linear. So if you notice also, if from this example, you see that our assumption is that it is linear from the graph. So if this is curved, then we cannot really get the exact value. But if we make the m increase, if we increase the number of panels, so the lesser the distance between them, so the better the approximation. Okay, so because we will avoid the error, no? So if m approaches infinity, although there's no infinity, so we will approach the exact value. Okay, so that's why the greater the m, the greater the accuracy. Later on we will talk about it. And okay, so we simultaneously create we create simultaneous equation out of these expressions here, no, in the differential equation. So meaning we measure individual y prime at individual points, and also y double prime, whichever the problem is looking for, no. So for example here, okay, so the very simple example for the 2-point boundary equation is the second order differential equation. So why is it why is it so with the boundary conditions, okay, ya is equal to a and yb is equal to beta, or okay, another set which is y prime a is equal to alpha, or y prime b is equal to beta. So or meaning it can be this first set, this is the first boundary, or this boundary. Okay, so if you can think of this problem, so you can think of the acceleration. So the acceleration is a function of the time x. Okay, so we change the x as time, y as the displacement, and then y prime is the velocity. This system, this can be bounded by the distance a alpha to beta, or the velocity. Imagine the car is bounded by a certain velocity, like from 0 to, let's say, 100 kph, because your car can only be operated from 0 to 120, for example, kilometer per hour. So that's bounded, no. So if you define the boundary, then you can easily solve for the dynamics, or the problems of the dynamics of the system. Okay, now approximating the derivatives at the mesh points by finite differences. Okay, so take note of this. We just simply substitute the this expression from this one. Okay, so you have here the y double prime, and then a function of x, y, and then this one, y prime. Okay, so this is very important. Okay, so we apply this expression to each of the mesh. Okay, so you see this is 1, 2, 3 until m, except the last, or this temporary variable. Okay, now arranging the above expression, we have m identically spaced some intervals, no. So this is the step 1. Okay, the step 1, we have defined the intervals, right? And it's very simple. Okay, so here we have from I is equal to 0, this one is I equals to 0. So at I is equal to 0, replace everything by 0, I equals 0. So this will be your expression. Okay, I hope you get this point, or this equation. So this one is when I is equal to 0. If you look at xi, that's x0, y0, and then this is 0 plus 1, so y1, and then minus y negative 1, then over 2h. Okay, and so then you have this one here, and if you notice, there's quite a bit of change. You have y1, 2y0, and then the h squared is transferred actually to the other side, no. So the h squared is cross multiplied here, so that's become h squared f, and then this expression here is transposed to the other side. Okay, so I think you got my point, no. So meaning this numerator here is retained, and then h squared is transposed to the other side, so that becomes equals h squared, the function of here, and then you transpose to the other side, so that becomes negative. and then equals to 0. Okay, I hope you got this point, no? And then if we go to I is equal to m, okay, I is equal to m, so you have this expression. Almost similar for the first equation, wherein you have I is equal to m from this expression, okay, and you have m minus 1. And then the same minus h squared, similar to this first equation, and then substitute all of this, okay? And then in the middle, okay, so this is the first boundary, and then this is the second boundary, and then the panels in between the two, so this one here in between, okay, so it's expressed, or the mesh at every point in between the boundary, so 1 2 and this one here, you know, so it can be expressed by this expression. So that's why if you notice, I is equal to 1 to m minus 1, so 0 is not, because this one here is I is equal to 0 and this one here is I equals m, so this one is 1 2 to m minus 1, okay, in between the two boundary. So substituting the respectively the I, or I mean, so you just transpose h squared and then transpose to the other side, so you have this expression. Okay, you see, it's very simple, no? Okay, now how do we apply this? Now if you have a problem, if you have later on we will give an example, if y double prime is equal to 1 minus sine x, okay, so you replace the function here with 1 minus sine x respectively, no, according to their variable inside. Okay, so we will see that one. So but I hope you try to understand this expression. Okay, now so we're done with that, no? And then since we know the boundary conditions, okay, here we're given with the displacement y0, which is alpha, and ym is equal to beta, meaning this value here can be replaced by alpha and beta. So if you go in the previous y prime, so y prime y prime is equal to alpha, and then uh, y prime of b is equal to beta. Okay, so I think I made a mistake. If this one is for the 0th degree and this one is the first degree, so as I said, it can be this first boundary or this second boundary. Okay, so some problem, okay, that's why there's can be two possible equations. So this one, if your first boundary is ya in the first 0th degree, okay, so you have this, if you replace alpha in the above expression here, okay, alpha is if y of a is equal to alpha, so you have alpha, and then you will understand that you will have then this equation, and then the inner equations, which is composed of the other panels, is retained, no? Okay, it's retained. And then for the last boundary, so it can be ym minus beta is equal to 0, or this a bit complicated expression if you're given with y prime of b or equals to beta. Okay, so it can be this one here and this one here and also this one here, or the second one, which is this expression here and expression here, and then this expression here. There you will have the simultaneous equation. Okay, simultaneous equations. So it may be a bit difficult for you to see, but let's try an example. So one of the example is you have the solve for the second order differential equation with linear boundary for m is equal to 10. So before we proceed with the calculation or the coding, so let's try to derive the expression. Okay, so and then we will stop before we proceed, no? So given this expression, I have written it here. Okay, so perhaps we can zoom a bit. Okay, and remove this one. So okay, given your expression y double prime in an example, so you have think we can move a bit here. Okay, so you have the of uh, f of x, y, and y prime is equal to negative 4y plus 4x. Okay, so therefore there's no y prime. Y prime is not in the function. So meaning this is your y double prime, right? Okay. For this first equation, our boundary, if you look at the if you look at the boundary, we're given with the 0th degree, and then the other one is in the first degree. Okay, so meaning we will use this first here, the first one here, okay, and then the second one here. So meaning we'll choose this one and then this one because of the given expression here. Okay, that's the given. So therefore we will use, and of course we will use this one. Okay, so let's derive first the simultaneous expression. So since we're given with y of 0 is equal to 0, so therefore and also, sorry, let me write first the pi over 2 is equal to 0. So first equation here, okay, so you have y of 0 minus, now if you notice alpha here is 0, so minus 0 is equal to 0, therefore y of 0 is equal to 0. Okay, and then let's proceed first to the m equation. The m equation, so you have, okay, 2ym minus 1, so you just simply write the 1 minus 1 minus 2ym minus h squared, then the function. Now if you notice the function, beta is for y prime, right? Y prime, but in your expression there's no y prime here. Okay, if you notice there's no y prime in this expression, so therefore you just simply copy that one, negative 4y plus 4x. Okay, and then you have plus 2h beta, and then beta is actually 0, so it is actually 0 plus to 0. Okay, so I hope you get that, you get this expression here. Okay, and to simplify this one, you have you just arrange this expression here, and actually this one is ym and xm. Okay, so you put all the x on the right hand side and all the y on the left hand side, so you have 2ym minus 1, then here negative 2, and then you have the negative 4ym, so you have plus ym, so I have negative 2 minus plus h squared 4h squared. Okay, and then that's ym, and then for the x we put in the outside, no, so we have x here, negative h squared times 4xm, so transpose becomes positive, so this is 4h squared, and then you have xm. Okay, so that's your equation. And then lastly, to end this part, you have the expression here, which is the one in the middle. You can see from this side in the left, so you have y I minus for m, for I, or the rest. Okay, so you have this expression y I minus 1 minus 2 yi plus yi plus 1 minus h squared, and then the function you just replace negative 4y I, and then plus 4xi, and then there's no y prime, and then minus 2h alpha, but alpha is 0, and equals to 0. And if you arrange this one, you have yi minus 1 minus 2y, all y prime. So maybe I will put plus. So negative 2 plus 4h squared, and then transpose the x on the other side, so you have negative h squared and plus 4 times, so you have positive 4h squared xi. Okay, so if you notice, they have almost similar with the previous one here. Okay, almost similar. I think I missed one thing. Why I forgot this one, this expression, sorry. I think I plus 1, so I forgot the plus y plus y I plus 1. Okay, so almost similar, except that this one here, we have additional. And with this, you have the simultaneous equation. We have this one. So these are the next expression. So number 1, okay, this one here, and then this one here. Now, given the number of equations, there are one, sorry, this one is may not be counted because y already has a value, no? So we just count here how many equations. So this one here, so we have m minus 1 plus 1 equation. So this is m equations. And how many variables we're looking for? Okay, so y I, so I is equal to from 0 to m. So this is therefore m plus 1 equations. Now, actually, sorry, variables, m plus 1 variables. Now, we also add plus 1 equation for the y0 here. We have 1 equation, so plus 1. So, so the number of equations is equal to the number of variables. Okay, because of this one here, and also actually because of this here, because of the beta. Otherwise, if there's no beta in the second expression here, sorry, I hope you can see from the screen. If you from this given expression here, if there's no beta in the second boundary, we will be lacking with the number of equations to reach the number of variables. Then if we have the same number of equations with the same number of variables to find all the yi, okay, then we can solve the problem, no? We can solve for the differential equation, because once we get all of these, okay, once we get all of this expression, then you can solve for y double prime, going back to the problem. So you can solve for y double prime equals to f. You can solve this. And this one, in this example, we have negative 4y plus 4x. We can solve all of this because if we go back to the expression, this is simply yi minus 1 minus 2y I plus yi over h squared, from I is equal to 0 to 1 to m, 1 to m. Okay, you just simply sum all of this, and then you have an accurate or approximated value of your y double prime. I hope you got this point here. Okay, so from I to m, so meaning you just simply add individually. Okay, so if you get if we will get these values here from the simultaneous equation, then we can solve for the y double prime. Okay, given the boundary. So that's very simple. I hope you got my point, and I think it's a bit time, so we can stop from here, and we will continue in the next live session for the actual code and example that you can relate. Okay, so this will end. Our live session will end now, and if you have questions, just let me know. Thank you so much.